Welcome to a deep dive into, well, your own body. Because, if you were to sneak a peek at your medical records right now, you probably assume the language in there is perfectly precise,
Right.
like a flawlessly engineered machine.
Oh, for sure. We certainly want medicine to be this realm of absolute, binary clarity. When a doctor writes something down, the assumption is that the terminology has been scientifically standardized for maximum accuracy.
Right, like every word is doing exactly one job.
Yeah.
But when you actually start digging into that terminology, especially how we talk about the cardiovascular system, you discover this hidden linguistic turf war happening right there on the page.
A turf war that's been going on for a very long time, yeah.
Exactly. And our mission today is to unpack two etymological twins from medical terminology. And those are angio and vaso. Now, at first glance, a medical dictionary tells you these both just mean blood vessel. But if you swap them in a hospital, you will end up saying complete nonsense.
Absolute nonsense, right?
So we are going to figure out how two ancient words that mean the exact same thing became entirely separated in modern medicine, creating this wild web of historical accidents and, honestly, massive misconceptions.
Yeah. And to understand how angio and vaso divide the territory of your body today, we really have to look at how they drifted apart in the first place. Because they didn't merge into one unified medical language at all.
No, they didn't.
They specialized in very distinct ways, and a lot of blood was spilled, figuratively and literally, to get us to this exact point.
Well, before we get into the complex history of blood and hospitals, we have to start with what these words meant before doctors claimed them. And honestly, this explains the absolute biggest mistake people make with them today. Because originally, neither of these roots meant blood vessel at all.
No, they didn't. If we strip away the modern clinical context, both angio, which comes from the Greek word angion, and vaso from the Latin word vas, originally described just a hollow, walled conduit.
Like a pot or a jar.
Right, a pot, a jar, a generic container that holds something, nothing more specific than that.
So let's put an analogy on this for you listening. It's kind of like the word receptacle, right? A trash can and a Tupperware bowl are both receptacles. They're both containers. But you wouldn't, mix up what goes inside them.
I would hope not.
It seems like early anatomists just used these words to mean some kind of tube long before the language became strictly associated with blood.
It's true. And that generic origin, it actually traps first-year medical students to this day.
Oh, the ultimate first-year trap.
Exactly. A student will have the term vaso drilled into their head as meaning blood vessel over and over, but then they get to the reproductive system and they encounter the vas deferens.
Right, and the vas deferens is the biological highway that carries sperm from where it's stored in the epididymis to where it ultimately exits through the urethra. It's a reproductive structure. It has absolutely zero to do with blood.
Nothing at all. It is purely a vessel in that ancient generic Latin sense of a container or a conduit. The reproductive tract basically borrowed that generic word centuries before the vaso prefix became modern clinical shorthand for blood physiology.
Which has real-world implications for how we understand our own medical procedures. I mean, it means that a vasectomy, which is the surgical interruption of that vas deferens tube for male sterilization, has literally nothing to do with blood vessels.
Even though it has veses right there in the name.
Right. So it perfectly illustrates how language evolves through historical convention rather than strict logic. But, the generic origin of these words doesn't explain why one ended up meaning plumbing and the other meaning pressure.
No, for that we have to take a trip back to ancient dissecting tables, where the fundamental rules of our bodies were fiercely debated.
Because we have this etymological split. On one side, we have angio, which is Greek, rooted in the Alexandrian anatomical tradition. And on the other, we have vaso, which is Latin, anchored in Rome, and later the Renaissance.
Right, so let's start in Ptolemaic Alexandria around 300 BCE. That environment was completely unique in the ancient world because it was the only place that permitted the systematic dissection of human cadavers.
Wow, the only place.
Yeah. And this is where we find Herophilus, who's often called the father of anatomy. He was the one who systematically distinguished arteries from veins, noting a structural difference. He saw that arteries had noticeably thicker walls.
Which is a crucial distinction. But Herophilus had a rival working right there beside him in Alexandria, a guy named Erastitus. And Erastitus proposed that arteries didn't carry blood at all.
Right, which sounds crazy to us now.
Yeah, he believed they carried pneuma, a vital spirit, or air, pumped directly from the heart. He thought blood only entered the arteries when they were damaged, basically leaking over from the veins through invisible connections.
Yeah, to a modern listener, the air and arteries theory sounds completely absurd.
Okay, hold on. I have to jump in and defend Aristidus here. We really can't laugh at him for this.
Fair enough.
Because think about the mechanics of death. When a person dies, their heart stops pumping, and their blood pools into the lower pressure venous system due to gravity and vessel relaxation. So when those ancient anatomists were dissecting recently dead bodies in Alexandria, the arteries in those cadavers were actually empty.
They were just looking at what was in front of them.
Exactly. For the technology he had, that was brilliant observational science. He just drew the wrong conclusion from a post-mortem artifact.
That is a very fair defense, and, it explains why the pneuma error persisted for roughly 4 centuries. It wasn't until the Roman physician Galen, working in the 2nd century CE, that the record was finally corrected.
And Galen favored the Greek vocabulary, right?
He did. He heavily utilized incursion, and he proved his point by performing ligation experiments on living animals. So he physically tied off sections of an artery in a living subject and showed that blood, not air, filled the vessel on both sides of the tie.
So he proved it was blood. But Galen, well, fixing one massive error, introduces an absolute blunder of his own, doesn't he?
Oh, a massive blunder. One that held back medicine for over a millennium. Galen proposed a model where blood was continuously manufactured in the liver from digested food.
In the liver?
Yep. He believed it flowed outward through the veins in an ebb and flow tide to be basically consumed by the body's tissues. And to account for the left side of the heart, he claimed a small amount of blood seeped over from the right side through invisible pores in the thick ventricular wall.
Invisible pores. I mean, when you feel your pulse on your wrist today, you just take for granted that blood is circulating in a loop. But for 1,400 years, if a doctor felt your pulse, they thought your liver was just pumping out a fresh one-way tide of blood that your tissues were eating.
And that liver-centered, non-circulating model dominated European medicine essentially unquestioned. It really wasn't until the Renaissance that the vas system was finally understood. In 1543, anatomist Andreas Vesalius openly doubted the existence of Galen's invisible pores.
And Vesalius used the Latin vas and vasa throughout his anatomical masterwork, right?
He did, setting the stage for the knockout punch, which came from William Harvey in 1628. Harvey also wrote in Latin, used vasa as his standard word for vessels, and he proved that blood circulates in a closed loop.
And the way he did it is my absolute favorite part. He used math.
The quantitative argument was revolutionary. Harvey simply calculated the volume of blood the heart pushes out with a single beat, multiplied it by the number of beats in an hour, and showed that the heart pumps a volume of fluid that exceeds the entire weight of the human body.
So the liver couldn't possibly manufacture that much blood out of the food you ate that day.
Not unless you're eating your body weight in food every hour.
Right. So it physically had to be the same blood going around and around.
It was a total paradigm shift. So coming out of the Renaissance into the modern era, medical English freely borrowed from both of those dead languages. We kept the Greek Angio and the Latin Vaso.
But, if they mean the exact same thing, why keep both? I mean, why didn't the medical community just pick one and standardize it?
Basically because as medicine industrialized in the 19th and 20th centuries, clinical usage organically sorted out a division of labor. It wasn't formally legislated by some medical board. It was historical accident that led to them splitting the territory.
And this is the modern split, which is just fascinating. Angio claimed vessel structure, imaging, and disease, while Vaso claimed vessel action and physiological behavior.
Exactly.
So think of it like a house. Angio is the plumber, physically replacing the copper pipes, but Vaso is the physicist calculating the water pressure and the flow rate through those pipes.
I love that analogy. Let's test it by looking at the plumbers first, the angio side of things, naming the physical structure and surgically altering it. A prime example is Charles Dotter in 1964, who is remembered as the father of interventional radiology.
His story is incredible. He had an 82-year-old patient, Laura Shaw. She had a painfully narrowed femoral artery in her leg, which was leading to gangrene in her foot. She was facing a full amputation, but completely refused the surgery.
Right, she said absolutely not.
So Dotter threads a series of graduated catheters, essentially small, flexible tubes, directly through the blockage to mechanically push the vessel open from the inside.
It was the very first percutaneous transluminal angioplasty. Let's break that jargon down. Percutaneous means through the skin. Transluminal means across the open space of the tube. Angio means vessel, and the suffix plasty means surgical reshaping.
So he physically reshaped the structure of the pipe.
Exactly. Her circulation improved, and her foot was completely saved from amputation.
And that structural focus paved the way for Andreas Grünsig in 1977. He performed the first balloon coronary angioplasty on a conscious patient, a 37-year-old insurance salesman named Adolf Bachmann.
Just incredible.
Imagine being awake while the doctor threads a tiny deflated balloon into a blocked artery in your beating heart and then inflates it to crush the plaque against the walls. Today, balloon angioplasties and the stents that keep those vessels propped open are performed over 1 million times a year worldwide.
Pure plumbing, pure angio.
Right, so now contrast that with the physicist side of the analogy, Vaso, dealing with dynamic action and fluid pressure.
Right, so in 1895, physiologists George Oliver and Edward Schaefer discovered that an extract from the posterior pituitary gland sharply raised blood pressure when injected into a subject. It did this by physically narrowing the blood vessels.
So they needed a name for it, and they named it strictly for its action. Vasopressin. Vaso for vessel and pressin for pressure, the pressor action.
It was later discovered to be the exact same molecule as antidiuretic hormone, which tells the kidneys to retain water. But the name vasopressin stuck because of that initially discovered vessel action. In the mid-1950s, biochemist Vincent Duvigneau actually synthesized it in a lab, work that grew out of the research that ultimately won him a Nobel Prize.
Wow.
It's a textbook case of vaso defining dynamic behavior rather than structural anatomy.
Okay, so we have this elegant division. Structure versus action. Plumber versus physicist. It is incredibly useful for categorizing medical knowledge. But there's a massive danger here. Relying too heavily on how we name something can create a biological blind spot.
It really can. And we see this vividly in the fight against cancer. The story of Judah Folkman perfectly illustrates the danger of that blind spot. In 1971, Folkman, who was a surgeon, proposed a radical idea in the New England Journal of Medicine. He hypothesized that solid tumors cannot grow beyond about 1 to 2 cubic millimeters without recruiting their own new blood supply.
Basically, they need a biological supply line to get any bigger. And he gave this process a very structured Angio name. Angiogenesis. Angio for vessel, genesis for formation or origin, the birth of new vessels.
Right.
His whole idea was if you can block that new vessel growth, you starve the tumor.
The oncology community met him with deep skepticism, though. He struggled for funding and was treated as a fringe figure for years. It was a 33-year wait from his original paper until February 2004, when the FDA finally approved the first anti-angiogenic drug, bevacizumab, better known by its brand name, Vastan.
So it proved that starving a tumor's blood supply could actually work.
It did. So, angio in its purest sense. Naming the structural growth, turning the name into a drug target, and it works. But the survival benefits weren't the absolute cure-all people hoped for.
Because biology fought back.
Exactly. Researchers discovered a highly counterintuitive workaround that tumors had evolved to survive these drugs. It's a phenomenon called vessel cooption.
Vessel cooption.
Yeah.
So instead of sprouting brand new blood vessels, which is exactly what the anti-angiogenesis drugs are perfectly designed to block, the tumors act like parasites.
Yes.
They just hijack and creep along the existing vessels that are already there in dense tissues like the lung, the liver, and the brain.
Blocking new vessel formation does absolutely nothing to stop a tumor from creeping along the vasculature that was already present in the organ.
Wait, so if the drug blocks new vessels, but the tumor just steals existing ones, does that mean our perfectly descriptive name, angiogenesis, actually gave us tunnel vision? Like, were we so focused on the genesis part, the creation of new pipes, that we accidentally tricked ourselves into thinking we understood the whole picture of how tumors survive?
It is a profound cautionary tale in medicine. We named the mechanism beautifully, and we successfully targeted the exact mechanism we named. But the vocabulary didn't capture the entire complex biology of tumor survival. Biology is, well, it's always more complex than our dictionary.
It really is. We've looked at ancient corpses in Alexandria, and we've looked at modern cancer drugs. But I want to bring this right back to you, the listener, because these two roots are dictating your daily physical experiences right now in ways that go far beyond just checking your blood pressure at the doctor's office. Let's look at the everyday vaso, the action happening inside you.
It is constant. Your vessels are dynamically changing diameter all day long. Let's take vasoconstriction, the active narrowing of the vessels. This is central to thermoregulation. When you step out into the freezing cold, the vessels in your skin constrict, pushing blood deeper into your core to conserve heat and protect your vital organs.
Vasoconstriction is also heavily involved in how migraines work, right?
During a migraine, blood vessels in the brain can painfully dilate, expanding and putting pressure on surrounding nerves. Some migraine medications work by aggressively forcing vasoconstriction, shrinking those vessels back down to normal size to relieve the throbbing pressure.
It's also exactly how nasal decongestants work. If
Yeah.
you have a stuffy nose and you take something like pseudoephedrine, it causes vasoconstriction of the blood vessels in your nasal lining. It shrinks that swollen, inflamed tissue so air can finally pass through and you can actually breathe.
On the flip side of that action, we have vasodilation, the active widening of vessels. If you are blushing from embarrassment, that rush of blood to your cheeks is vasodilation. If you are sweating and releasing heat on a hot day, that's vasodilation bringing warm blood to the surface of your skin.
Which is super important.
Yeah, and it's also the underlying physiology of erectile function, which is why many ED medications work by targeting and promoting vasodilation.
But sometimes this dynamic action malfunctions, right? One of the most common reasons completely healthy people pass out is called vasovagal syncope.
Yeah, this can be triggered by the sight of blood, sudden emotional distress, or even just prolonged standing. What happens mechanically is a sudden inappropriate drop in heart rate combined with a loss of vessel tone.
So they just give out.
Exactly. The vessels dilate when they shouldn't, blood pressure crashes, your brain briefly loses its oxygen supply, and you faint. The vaso fails to maintain the pressure.
Another really scary malfunction is angioedema. It's a severe swelling reaction. Sometimes it's an allergy, but it can also be a known side effect of ACE inhibitor blood pressure medications.
Right, which are very common.
Yeah, ACE inhibitors are designed to relax your blood vessels to lower your overall pressure. But sometimes they trigger this rogue reaction where fluid rapidly leaks out of the vessels into the surrounding tissue, causing massive swelling in the face or throat. It sends people to the ER regularly. And, since we're in the neighborhood of all these terms, let's quickly map out the surrounding terminology so you have the full toolkit when you look at those medical records.
Good idea. A good place to start is distinguishing the specific vessel types beyond the general prefixes. Arterio refers specifically to arteries, which, as Herophilus noted in ancient times, have thick, muscular, elastic walls to withstand the high-pressure surges of blood coming directly from the heart.
Makes sense.
And then phlebo and veno, another Greek and Latin pair, refer to veins. Veins have much thinner walls and use tiny one-way valves to fight gravity and prevent backflow as blood slowly returns to the heart.
And what about lympho? Because the lymphatic system runs parallel to our blood vessels, carrying immune cells and fluid.
Interestingly, the Angio route extends naturally into the lymphatic system. You will see structural terms like lymphangioma, which is a malformation of lymphatic vessels, but vaso almost never crosses over into lymphatic terminology.
Oh, that.
Because the lymphatic system is generally low pressure, so the dynamic action prefix doesn't apply as neatly. It's just another sign of that deep historical specialization we discussed.
And then we have the ultimate hybrid word, cardiovascular. It literally fuses the Greek word for heart cardia with the Latin word for vessel vas. One single word, borrowing from two ancient empires, naming your entire circulatory system.
It perfectly encapsulates the entire journey we've taken today. Two languages, Greek and Latin. One underlying meaning, a generic vessel or container.
Split by historical accident into the physical structure of our bodily pipes, Angio, the plumber, and the dynamic, pressurized action of the fluids rushing through them, Vaso, the physicist.
From Aristotle debating the presence of air in cadavers, to William Harvey doing the math to prove circulation, all the way to modern balloon angioplasties and targeted anti-cancer drugs, these two ancient roots have carried the entire weight of human medical discovery.
They really have. But I want to leave you with a final, surprising connection from our sources that shows just how far these roots reach. We mentioned at the very beginning that the Greek root angine originally just meant a jar or a generic container for a fluid or seed. Well, that root actually escaped human medicine entirely. The next time you look at a flowering plant like a rose, a daisy, an apple tree, remember that its scientific classification is an angiosperm.
Which literally translates to vessel seed or enclosed seed, because unlike pine cones, a flowering plant's seeds are contained within a protective ovary, a biological container.
A vessel. It is such a beautiful reminder that a flower blooming in your garden, an ancient Greek clay jar, and a modern life-saving heart stent all share the exact same linguistic DNA. So the next time you're trying to decode that hidden turf war inside your medical records, just remember, your body isn't just a machine. It's a living, breathing museum of human history.